You probably find your way around places every single day without even thinking about it. But what if I told you that the way we normally do it, that simple grid of over and up, isn't always the best way? Let's dive into a totally new way to map our world.
We're all so used to that classic XY grid. Go over this far, go up that far. It's simple, it works. But think about it. What about things that spin or move in circles? Like a radar dish sweeping the sky, or a planet orbiting the sun. Is a square grid really the most natural way to describe those things? It really makes you wonder, is that grid always the right tool for the job?
It's kind of like giving directions. You could tell someone, okay, walk 3 blocks east and then take a left and walk 4 blocks north. That's the grid method, right? The Cartesian way. Or you could just point and say, see that corner? Face northeast and walk 5 blocks. It feels so much more direct, doesn't it? Well, that second method, that's exactly what we're going to break down.
So that compass method actually has a formal name in math, and it's built on 2 really simple, intuitive ideas: distance and direction. Let's really get into what that means. Okay, let's meet the star of the show, polar coordinates, written as r theta. In this system, r is just the distance from the center, which we call the pole. And theta, that's the Greek letter theta, is the angle you rotate from your starting line, which we call the polar axis. So you can forget over and up. Now we're going to think distance and angle.
All right, now here's where things get a little weird, but really interesting. In pretty much all the geometry you've done so far, distance is always a positive thing. But in polar coordinates, r can actually be negative. So what on earth does a negative distance even mean?
It's actually a lot simpler than it sounds. If r is positive, it's easy. You just face the direction of your angle and you walk forward that many steps. But if r is negative, well, you still face the exact same direction your angle points, but you walk backward. You just move that distance in the complete opposite direction, 180 degrees the other way.
Okay, that's enough theory. The best way to really wrap your head around this is to actually do it. So let's get our hands dirty and plot some points.
First up, let's plot the point 3, pi over 4. So first things first, we handle the angle. We rotate pi over 4 radians, that's 45 degrees, from our starting line. Then we look at our radius, r. It's a positive 3, so we just move 3 units straight out along that 45-degree line. And boom, there's our point. Simple enough.
All right, that was the easy one. But now for that curveball we were talking about. What happens with that negative radius? This is where that walk backward rule is going to be super important.
Let's plot negative 2 pi over 3. Okay, first, the angle. We swing around pi over 3, or 60 degrees. That line points up into that first quadrant, but our radius is negative 2, so we don't move forward along that line. We do a 180 and we walk 2 units straight back, right through the origin. And just look where we end up. The big takeaway here is that the point can land somewhere completely different from where the angle is actually pointing. And that brings us to one of the most unique and honestly powerful things about polar coordinates. See, in the normal grid world, a point has one address. That's it. 3, 4 is 3, 4. But in the polar world, every single point has an infinite number of different names. They're like aliases.
And I'm not exaggerating here. I really mean infinitely many. Just think about it for a second. You can land on a spot, then just spin around a full 360 degrees, and you're right back in the same place, but you have a new angle. You could do that forever. And if you mix that with the whole negative radius trick, you suddenly have endless ways to name the exact same spot.
And there are actually some really clear patterns for finding these aliases. Let's take the point 4, pi over 6. An easy way to find another name is just to add a full rotation, that's 2 pi radians, to the angle. We land right back where we started, just with a new name. Or we can use that negative radius trick. Flip the r to negative 4, and then just add half a rotation, or pi, to the angle. You guessed it, we end up in the exact same spot. It just shows you how flexible this whole system is.
So why are we even bothering with all this, with these aliases and negative distances? Is this just some weird math puzzle? Not at all. The real world is absolutely full of things that operate on polar coordinates, even if they don't call it that.
Just listen to how an air traffic controller might talk. Flight 247 is at 12 nautical miles bearing 045 degrees. What did they just give you? They gave you a distance, 12 miles, and an angle, 45 degrees. That is a polar coordinate. They're literally describing a point using r, theta.
And there's a really good reason for it. Radar systems are built from the ground up to work this way. The antenna spins around to find the angle, theta, and a radio pulse shoots out to measure the distance, r. It's not calculating some x and y position, it's measuring distance and direction directly. For a job like that, polar coordinates aren't just a different way of doing things, they are the better way.
So as you start playing around with these, let's just go over a few key things to watch out for. These are the spots where people usually get tripped up, but if you see them coming, you can navigate them like a total pro.
Here's your little pre-calc checklist. First, always remember that negative r rule. It flips the point straight through the origin. Second, keep an eye out for those aliases. Don't just assume 2 points are different because their coordinates look different. And finally, watch your units. Most advanced math, especially in calculus and physics, is going to use radians, not degrees. So it's a really good idea to get comfortable with them now.
You know, when it comes down to it, learning polar coordinates isn't just about a new way to plot points in math class. It's really about learning to see things from a completely different frame of reference. It proves that sometimes the best way to understand something is to just change your point of view. So the big question to leave you with is this. If we can see something as simple as a point from a whole new perspective, what other complex ideas out there can we look at from a new angle?